Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at sampling distributions. These are distributions of statistics. So whether or not something constitutes a statistic or a parameter depends entirely on whether it is from the sample or the population. So recall, population is everybody to whom a characteristic applies, and a sample is some of them. So let's say, for example, I wanted to know about how many hours per night students study. This mu would be the mean of every student. X bar would be the mean of just some students. Sigma is the standard deviation of all the students, and S is the standard deviation of just some of the students. Of course, I might only take a sample because it would be very time consuming to ask every single student how many hours a week they spend on homework. So as I said, statistics have their own distributions, and these are called sampling distributions. In this video, we're going to look at the sampling distributions of the sample mean and also the sample proportion. So central to this is the central limit theorem. If you have sufficiently large random samples, usually that means n is greater than or equal to 30, then the distribution of sample means is approximately normal. Remember, n is the sample size, the number of observations in your sample. So what we're saying here is if you have a sample size greater than or equal to 30, then the sample mean has its own distribution that happens to be normal. So the mean of that distribution is mu, the population mean, and the variance of that distribution is sigma squared on n. So what's really interesting about the central limit theorem is that the original distribution doesn't matter. So here we're looking at taking a sample mean from a set of data. That set of data has a distribution, but it doesn't matter if it's not bell-shaped. It doesn't matter what it looks like. The central limit theorem will still apply. So let's look at a question like this. Suppose that 15-year-olds at our school sleep for a mean time of 7.86 hours. So because we're assuming that this is the mean of everyone at the school, 7.86 here is mu. And we're assuming that the standard deviation is 1.2 hours. Here that is sigma because it's the population. It refers to everyone at the school. So if I select 50 at random, calculate the probability that the mean of this sample will be greater than 8 hours. So we know here that the sample mean is normally distributed. The mean of this distribution is mu, which is 7.86. And the standard deviation is 1.2, so the variance is 1.2 squared. So if we want to find the probability that a particular mean is more than 8 hours, we will convert that to a z-score. So we have z equals score minus mean. Now that part hasn't changed, but what goes on the bottom kind of has. See, this value sigma is not the standard deviation of the sample mean, it's the standard deviation of each of the individual scores. What we need to put here is the square root of that. So that's actually called the standard error. So the square root of sigma squared on n, we can just simplify that to sigma on root n. That's what's going to go on the bottom here. So we put on the bottom sigma over root n, and we can put this straight on our calculator. And so we get z-score of about 0.825. So now we need to find the probability that z exceeds that. So of course, if we're using tables, we can't calculate directly the probability that z exceeds a number. We can only calculate the probability z is less than a number. So we use this here. So whether we use the table or we use technology, we have that the probability of z being less than 0.825 is about 0.795. So that gives us a final answer of approximately 0.205. So there's about a 20.5% chance that we would end up with a mean greater than 8 hours. You can see this is quite a low probability, even though this was very close to mu. Of course, if we're looking at scores that are very different from the mean, it's far more likely that that will happen with a single observation than from a mean of 50 observations. All right, let's now look at proportions. So when we're talking proportions, this is the sample proportion, this the population proportion. This is a statistic, this is a parameter. So p hat, the sample proportion is x over n, where x follows a binomial distribution. The sample proportion is just the number of successes divided by the total number of trials. So it turns out that, like the sample mean, the sample proportion follows a normal distribution approximately when conditions are met. Now, this shouldn't come as a surprise because x is basically just a mean. It is just a mean where you have a score of 1 for a success and a score of 0 when it's a failure. So if I wanted to find, say, the proportion of students that had blue eyes, we just give a 1 every time a student has blue eyes and a 0 when they don't. So it's pretty much just the mean of a long string of scores that is 0 or 1. So predictably, p hat becomes more and more normal as the number of trials, n, increases. When you have a small number of trials, you might get a probability distribution that looks like this, but as you increase the number of trials, it always starts to look more and more normal. But when we're talking p hat, we have these two additional conditions here. So why is that? Well, the thing is, when we're approximating p hat with a normal distribution can theoretically take any value between negative infinity and positive infinity. However, we know that as a population proportion, p hat always has to be between 0 and 1. Now, the expected value of p hat is p. I mean, that makes sense. If there's 30% of students at the school with blue eyes, I expect that if I take a sample of them, 30% of my sample will have blue eyes. And of course, p hat might not be halfway between 0 and 1. So these two may not be the same distance from p, but what we want to do is we want to make sure that the probability of being less than 0 or more than 1 is very, very low, because being less than 0 or more than 1 is possible with a normal distribution, but impossible for p hat. So if we require that each of these is true, what it means is that the absolute worst case scenario, this will be 3 standard deviations from p, and this will be 3 standard deviations from p. So that means that the worst case scenario is that you have 0.15% of scores outside the range 0 to 1 when you approximate p hat with a normal distribution. And of course, this number comes from the rule. Remember that in any normal distribution, 99.7% of scores are within 3 standard deviations of the mean. So with all that in mind, why would we actually want to approximate p hat with a normal distribution? Well, it does go back to the old days. See, if x follows a binomial distribution, this is the probability mass function. Now, it turns out calculating n choose x can be a bit problematic. This is the formula for n choose x, if you recall. It requires factorials. So if n is a large number, that can cause problems. Now, modern computers are getting very good. They can handle calculations of large factorials. Sometimes, even today, you might have a sample size of about 1,000. 1,000 factorials, say, way too high for the Google calculator to handle. So that's why the normal distribution is still used as an approximation for the distribution of p hat. Let's look at a concrete example. So suppose at our school, proportion of students born overseas is 0.4. I randomly select 30 students. We're going to calculate the probability that between 10 and 20 will be born overseas. So it's not clear from the question, am I calculating this or am I calculating that? Now, in a normal distribution, these two would yield the exact same probability. However, when we're looking at the binomial distribution, you can get very different answers from these. So what we need to do is apply a continuity correction. So that is, we reduce the lower bound and increase the upper bound each by 0.5. Instead, what we're actually going to calculate is this. We're going to reduce 10 by a half, and we're going to increase 20 by a half. So what that will do is get rid of the ambiguity that I just spoke about. It's called a continuity correction because we're approximating a discrete random variable with a continuous random variable. Now note also here that if I sample students, I'm really going to do it without replacement. I'm not going to sample the same student 30 times. But the binomial distribution requires that the probability is the same each time. But if I pick someone who was born overseas, the probability that the next person was born overseas is going to be slightly less than 0.4. But what we can do is use the 10% rule. If we sample less than 10% of the population, we can ignore the without replacement, what I just said. Because the probability calculations are so similar, they'll be very, very, very close. So at our school, there is over 1,000 students, so 30% is well under 10% of the population. So that's why I can ignore the distinction between with and without replacement. So what I'm going to do now is convert each of these x values into p hat values. So n was 30. So I want to find the value that p hat is between 9.5 over 30 and 20.5 over 30. So I can use a normal distribution. This will be the mean, and this will be the standard deviation of such a distribution. Note, this is the standard error of p hat. So the expected value of p hat is 0.4, and the standard error is p times 1 minus p, all divided by n, and then square rooted. So with that, I'm now going to convert each of these to z-scores. So note, in each case, I took the value of p hat minus p divided by standard error. For the first, I get about minus 0.93, and for the second, I get about 3.1. So I've reduced this to a z distribution. I want to find the probability z is between these two values. So using either a table or technology, it's approximately 0.9992 for the first. The second one's about 0.1762. So we end up with about 0.823. So there's about an 82.3% chance that I will have between 10 and 20 students born overseas in my sample. Now, we probably should have done this at the start, but just to double check that NP and N1 minus P satisfy our definition, in this case, NP was 30 times 0.4, which equals 12. I don't really need to try n times 1 minus p, because 1 minus p is more than p. I'll get an answer more than 12. NP and N1 minus P are both more than 9, so that means that my assumption that P hat was approximately normally distributed is valid. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.